Hello everyone, welcome to this video. In this video, let us see the next concepts of analog and digital communication chapter, that is transmitter, modulation, channel or medium, noise, receiver and destination. The modern communication system scheme we have seen in the previous video, where we will be having an information source that will be called as message. Then information source will be having a message that need to be converted into an electrical quantity. So we need an input transducer that will be called as a baseband or message signal. So that will be given to the transmitter. This transmitter will be having a modulator or encoder, we can say. So the output of the transmitter will be a transmitted signal and that will be given to the channel or medium. There might be a chance of inclusion of noise. So the output of channel will be received at the receiver, and receiver output will be recovered signal, means it is a baseband signal what we have sent from the transmitter end. So output transducer will convert that into a physical quantity. That will be the original message. This we have seen. Here in between we have mentioned those signals in terms of time. Means the output of the transducer is electrical quantity that will be represented as S of t. Output of the transmitter is X of t. Output of the channel is R of t. And again at the receiver we will be having S of t, that is what the transducer output here is. So let us understand this transmitter part now, what this transmitter is going to do. Transmitter is a section that processes the baseband signal prior to the transmission, means before transmission we are modifying that signal that transmitter is going to do. The nature of processing depending on the type of communication. Here what is the type of communication we have? There are two types of communication. One is a carrier communication, another one is a baseband communication. What do you mean by a baseband signal? Baseband in the sense it is a message signal which is in terms of electrical quantity. What is carrier signal? Which is an additional signal we are giving as with a baseband signal. So carrier communication in the sense the baseband signal which lies in low frequency spectrum translated to a higher frequency spectrum. So here modulation comes into picture. We are going to use a technique called modulation. Modulation is the main function of the transmitter in carrier communication. In baseband communication, there is no concept of carrier itself. So there is no carrier means there is no modulation. So we say carrier communication and baseband communication are the two types where we are going to do modulation in carrier communication. Generally we will be following this communication method. Baseband communication is not preferred. Why? Because it is difficult to transmit to a longer distance. So we need to understand modulation now. What is modulation then? Modulation is a process of changing the behavior of the carrier with respect to the baseband signal. So here in other words we can say the message signal or baseband signal is superimposed upon the high frequency carrier. Means understand, here this is my baseband signal which is having low frequency and this is my carrier signal, it will be having high frequency. Now I am superimposing my baseband signal on the carrier. This will be called as modulation. Why modulation is required means because of the low frequency baseband signal, we can't transmit this baseband signal to a longer distance. High frequency signal will be transmitted to a longer distance. So we are passing this baseband on the carrier and this carrier signal will be sent with the baseband to a longer distance. So we can achieve that using modulation. The original message signal cannot be transferred over a longer distance because of the low frequency and amplitude. They are superimposed on the high frequency carrier signal so that we can achieve the distance. So in the longer distance communication we are going to use carrier communication. Here you can see this is what the baseband signal is. Here it is not given as a sine wave, it is a square wave. Here it is given. No worries, just try to understand. If it is a square wave is our baseband signal and we are considering this is our low input and this is my high input. A method of making this signal to a high frequency signal is that in low values I am treating it as a low frequency. In high values I am changing the frequency into high frequency component. You can observe here this is having a low frequency, this is having a high frequency, correct? So low frequency signal when it is low value When it is high value, we can say it is high frequency signal. Similarly, if it is low again, it is a low frequency signal. Similarly, when it is high frequency signal. This is a method of making the low frequency baseband signal convert into a high frequency signal. Okay, let us understand this concept while discussing digital communication concept. Now we are concentrating on the analog communication part. So this is my analog signal. So this is my analog sine wave, which will be called as a message signal, or it will be called as a baseband signal. Okay, this baseband signal will be having low frequency. And this is a carrier signal. This carrier signal will be having high frequency. And this is my modulated signal. Modulated means after modulation. So this will be called as a modulating signal. Modulating means I am still modulating this signal with a carrier. So I am going to get a modulated signal after superimposing these two. So this is what modulation is. Here you can observe in the modulated signal there will be a change in the frequency over here, and here the frequency is high, frequency is low, again frequency is high, depending on the message signal or the baseband signal what we have. So let us understand it in more detail. So if baseband signal is analog, analog communication method is applied, we call it as analog communication. If the baseband signal is digital, we apply some digital communication concept and it will be called as digital communication. So this is the block diagram of the transmitter now. The main functionality of the transmitter is that it is doing modulation. This is the main function of the transmitter. So baseband signal is an input which will be called as S of t. Here we will be having modulated stage. This is what the modulation stage. For modulation we require a high frequency signal. This carrier signal is high frequency signal. This is C of t. This baseband signal is low frequency signal, and we are going to do the modulation here using these two signals, low frequency and high frequency. The output will be called as X of t. This is obviously an high frequency signal, and that will be given to the amplifier stages. So we need to increase the amplitude. So sufficient amplitude is required to transmit to the channel. So voltage amplifier stages are there in the first stage, and at the next stage we will be having power amplifiers. Power amplifier is that it is going to increase both voltage and current. P is equal to V into I. If we increase voltage as well as current of the signal, then it will be called as power amplifier. Some amplifiers may be having a current amplifier or voltage amplifier. So power amplifier is going to amplify total voltage as well as current. Then we are going to give it to the channel. So basically what we have understood here, the main function of the transducer is modulation, and then it will be having amplifier stages. This will be called as a transmitter. So modulation is a process of changing the amplitude, changing the frequency, or changing the phase of the carrier signal. Okay, we are going to change the amplitude, frequency, phase of the carrier with respect to the baseband signal. Okay, we are not going to change the baseband. This is our original message. We are not supposed to alter any frequency, any amplitude of the baseband signal. We need to alter the carrier according to the baseband signal taken as reference. That is what modulation is. We can change the amplitude, or we can change the frequency, or we can change the phase. When we are changing amplitude, we are taking these two as constant. We are not going to alter. We are going to alter only amplitude. Then it will be called as AM. Suppose if I am altering frequency, I am keeping amplitude and phase as constant, it will be called as FM. Suppose if I am varying the phase of the carrier with respect to the baseband, keeping amplitude and frequency of the carrier constant, it will be called as PM. Okay, amplitude modulation, frequency modulation, and phase modulation. So modulation in the sense, we will be having a input, means baseband signal, we will be having a carrier signal, high frequency. It will be modified into these three signals. It can be AM if the amplitude of the carrier is varying. You can observe here, this is the amplitude of the carrier. Now it is changing with respect to the input signal, means with respect to the baseband. Here it is high, here it is low. That's why carrier amplitude is high here, and when the baseband signal amplitude is coming less, carrier signal amplitude coming less. This is AM. FM, you can observe according to the baseband signal, wherever it is having a high voltage, the frequency is high. At the low voltages, the frequency is less. So this is FM. We are changing the carrier, we are not changing the baseband. Here also in the phase, it is not clearly showing here. The phase is changed here from positive negative values. So this is phase modulation. This is what the main concept of modulation, where we are altering the carrier frequency with respect to the baseband signal is considered. But this carrier frequency is a high frequency signal, baseband signal is a low frequency signal. And then suppose if we take an example of an radio frequency communication or radio broadcasting, we can say. In radio broadcasting, we will be having a sound as input. It will be having sound in the audio range. Then we will be having a microphone that will be converting our sound into an electrical signal. Here it will be a transducer. So we are going to do some modulation. So modulation, we require a carrier signal. Here the carrier frequency is in the range of radio frequencies. Radio frequency is a high frequency. The sound frequency is very less. Audio frequency is very less. So we need to modify that with respect to the radio frequency is concerned. So modulation is done and then it will be in the RF range. So whatever the carrier frequency is, the modulated signal frequency will be with respect to the carrier, not with respect to the baseband. But the amplitude, phase as well as frequency of the baseband signal is not going to be varied. We are going to vary the carrier amplitude, carrier frequency, carrier phase. Any of these three can be varied. Only one, not all the three. So RF baseband band spectrum will be in the range of 30 kHz to 300 GHz. So transmission systems are operated with the RF spectrum range, including analog radio. It will be used in aircraft navigation, marine radio, armature radio, and also in TV broadcasting, and then in mobile network communication and satellite communication, which are all the things where we are expecting it as a wireless communication through air, where we are going to use RF. Here is the set of radio frequency ranges. You can observe where if it is 10 to 30 kHz, a low radio frequency, we call it as VLF, very low frequency. It will be used in point-to-point communication. If it is more than 30 up to 300 kHz, we use it in navigation, and it is also called as low frequency class. And 300 to 3000, it will be called as medium frequency. It is used in radio broadcasting. And 3 to 30 megahertz, it is high frequency, called as overseas radio broadcasting. And 30 to 300 megahertz VHF, very high frequency, it is used in television and FM broadcasting in radar. You can observe these FM channels what we have will be having a frequency in megahertz. And then UHF, that is ultra high frequency, 300 to 3000 megahertz, that is used in again in television and navigation. 300 to 30,000 megahertz, where it is SHF, super high frequency, it is in radio navigation and radio relays we are going to use. You might have observed in old TVs, if you have, when we are tuning the channels, we will be having UHF, VHF and HF signals. So those channels are going to be having a frequency of VHF, UHF, and we are going to tune that. That is what the meaning here. And this is again another approach of explaining the same thing in navigation, in marine, as well as in radio, FM, AM, and VHF, UHF, as I said, in the TV channels we will be getting in these frequencies. And then satellite communication and radio astronomy, satellite communications. These are the frequencies as well as the wavelength they have given. Okay, you can go through this. And then what is channel or medium? Channel means it is a medium through which message is going to travel, or the signal is going to travel from the transmitter to the receiver. This channel will come in between. This is a channel, and before that we will be having a transmitter, and next we will be having a receiver. So this is what our flow is. So channel is a medium, we can say. We can be having this channel in between the transmitter as well as receiver. So transmitted signal should have adequate power to withstand the noise in the channel. We know that noise is a parameter, it will be added with the signal in the channel. That's why whatever the signal we are getting out of the transmitter will be having high power. So because of this achieving a high power, we will be using a power amplifier at the output of the transmitter, right? And next we will be having the receiver. So the receiver should also have a power amplifier, so that whatever the noise it is added with the channel will be addressed carefully at the receiver. So there are two types of channels here. The two types of channels are hardwired channel and a soft-wired channel. What do you mean by hardwired channel? Means it is a man-made structure, and soft-wired channel in the sense it is a natural resource. Means if it is a twisted pair of cable what we use in telephones, that will be called as hardwired. And suppose an ear is an interface in wireless communication, that will be called as soft-wired. It can be having an antenna which converts electrical signal into electromagnetic waves in a soft-wired channels. So it can be a open space also, it can be a vacuum also, it can be a sea water also. If we are communicating through these channels, these mediums, it will be called as soft-wired. These are all the natural resources. We have not created those. So in the hardwired channel, we say there is a wire, a pair of wire is there, a coaxial cable is there, which will be used in the TV transmission. It will be carrying high frequency signals. And optical fiber communication means OFC. We will be having a light passing through a glass fiber or through a glass, we can say, using total internal reflection, using a light energy. So these are things which we have created to transmit the data using a wire, using a cable and using a fiber. This will be called as hardwired channels. Soft-wired channels in the sense, better example is air. Air interface is a soft-wired channel. And then what is noise? Noise is a thing which will be added with the signal while the signal is transmitted in a channel. This is what noise is. So we can say noise is a disturbance, or we say it is an unwanted electrical signal which is added up with the transmitted signal in a channel. So noise is highly undesirable part in a communication system. It has to be minimized. If more noise is added with the signal what we are transmitting, the information what we are sending may be degraded. So we need to address this noise carefully. So noise reduction technique is one of the important parameter we are going to understand. So when noise is mixed with the transmitted signal, it rides over it and distorts the waveform. Deteriorates antandre it is distorted. So what is signal to noise ratio? We will be having a parameter to understand what is the amount of noise included. So we will be having signal to noise ratio. This is the ratio of power of the signal to the power of the noise. What is the noise included and what is power of that will be taken in the denominator, and power of the signal what we are transmitting taken in the numerator. This will be called as signal to noise ratio. Signal in the numerator, noise in the denominator. So here PS is signal power and PN is noise power. So it is written as PS divided by PN. So what is PS? Power of the signal, we can write it as V square R, and noise power can also be written as Vn square R. So V square R divided by Vn square R. So here is Vs is the signal voltage and Vn is the obviously noise voltage, and R is that we are taking the dissipation of this power with the same resistor R. By considering this as R and the signal, if we are passing through this resistor, what is the power it is going to dissipate? That is what PS, if it is our input signal. Suppose a noise signal is included, the power of that is Pn. So in addition, we need to assume that both the signals and noise powers are dissipated across the same resistor, and signal to noise ratio can be expressed as in decibels. When we are expressed in decibels, if it is a power, we need to take it as 10 log of that power ratio. So here signal to noise ratio in dB is 10 log with respect to the base 10 Vs square divided by Vn square. Similarly, if you take out this square and towards this, it becomes 20 log. And for example, if you take a value of 3.5 millivolts and 0.75 millivolts is a signal as well as noise voltages. If we substitute, we will be getting 13.38 dB as our signal to noise ratio. This is the value saying the ratio between the power of the signal to the power of the noise. What happens if the noise power increases? If denominator increases, this value is going to be reduced. If denominator is less, if less noise is included, this SNR is more. So then we will be having one more parameter called noise factor. Noise factor will be represented as F. It is Si divided by Ni to S0 divided by N0. It means if we calculate SNR at the input side and if we calculate SNR at the output side, it gives the noise factor of which noise included. So one more thing is noise figure is NF, noise figure is equal to 10 log of the noise factor. If you give 10 log of that, it will be represented in dB. This is what noise factor and noise figure. And then we will be having a receiver. We have understood transmitter, and similarly we have receiver at the other end. At the user end, we will be having transmitter and receiver. One is sending, will be using a transducer. One is receiving, will be using a receiver. So here the reproduction of the signal is required. The original signal means the message or the baseband signal need to be retrieved. So we are going to use demodulation. If we use modulation in transmitter, we use demodulation in receiver. And it will be also called as detection. Demodulation is also called as detection. Demodulation is a reverse process of modulation. So here the received signal is represented as R of t. We will be having an initial amplifier stage to amplify this, since it is included with the noise and all. So we need to amplify. R of t is the output of this, and then we will be given to the demodulator. This demodulator requires an additional input of C of t, means carrier is required here. Whatever the signal we are going to use in modulator, a baseband signal with the carrier. Similarly here also in the receiver, while demodulating, we require a carrier again. So we need to take out the frequency of the carrier, and finally we are going to get only the baseband signal. This is the received signal. So we require carrier here also in the demodulator. So demodulation, the baseband signal is separated from the high frequency carrier signal, and after recovering the original baseband signal, that is S dash of t, its voltage power is amplified and then it is sent to the final destination. So we will be having amplifier stages here, voltage amplifier as well as the power amplifier. So final destination we are going to have at the output. In the final destination, again we will be having a transducer which converts an electrical signal S dash of t into a physical quantity. If it is an radio transmitter like that, we will be having an output through the speaker. Then destination. What is destination? Destination is a final stage which is used to convert an electrical message signal into a original form. Suppose in a radio broadcasting, the destination is a loudspeaker. We are going to get the speech what they have sent from the source, which works as a transducer and convert electrical signal into original sound. This is what the communication and the modern communication scheme having these steps. Here modulation is one of the important concept, and modulation, what we are going to do, we will be having a baseband signal and we will be having a carrier. We are going to superimpose this baseband on carrier and we are going to get the modulated output. This will be called as modulating signal, and it will be called as message signal. This will be called as baseband signal. This is carrier. And there are three types of modulation we can expect. One is amplitude modulation, another one is frequency modulation, another one is phase modulation. While doing the amplitude modulation, we are going to change the amplitude of the carrier with respect to the amplitude of the baseband signal. Here we are varying frequency of the carrier by keeping the other two constant. Here we are varying the phase of the carrier by keeping the other two constant. This is how the modulation and transmitter as well as receiver, again it will be doing the reverse functionality by using the carrier again. Thank you.